you. Before we start the seminar, I would like to tell you that this meeting will be lasting for only 40 minutes. So the meeting will be auto ends. So when it happens at the same at the time, you can join back to the same link. Okay. Yeah. So that's the thing that I wanted to say. Yeah. So let's start. So I'm going to share screen. Okay. I hope you guys can see my screen. Yeah. Okay. Write down the topic vectors. So, now let's begin. I should take this here and this like this. Okay, so understanding mechanics. Now, if we consider mechanics, I can say mechanics is the heart of physics because if we consider the heart pump blood to every part of our body, right? Similarly, the theories and the laws that we study in the mechanics were used and applied in every part of physics. Like if you take particle physics, mechanics, and all. So like in thermodynamics, electric field, electricity, magnetic field, astronomy, gravity, electronics, nuclear physics, waves, and quantum physics, and even particle physics. We use the theories and laws that we study in mechanics. So mechanics is very important. So to understand physics, understanding mechanics is crucial, right? Yeah. So to understand mechanics, we have to understand mechanics, we should know the basics, like fundamentals. So if we consider the basics, it is actually the physical properties, right? Sorry, it's not physical properties. Okay, I think I made a small mistake in while doing this presentation. It should be physical quantities. Yeah, should be physical quantities. Okay, so here too, physical quantities. Okay. I'm sorry for that. Okay, so yeah, I think you still can see my screen, right? Okay, so let's start from this page. So here too, it should be physical quantities. Okay. Okay, so all physical quantities we can categorize into two classes. One are scalars, the other one is vectors. So what is a scalar? Have you have any idea? I think you have already studied in your O-levels what are scalars and vectors. So scalars, we know they have only a magnitude, no? Scalar quantities. So scalars, or you can say scalar quantities. Scalar quantities have only a magnitude. And vectors, on the other hand, they have both magnitude and a direction. Vectors have both magnitude both magnitude and direction. Okay. Now, if we consider the scalars, so understanding the scalars is very easy because they have only values. So it is not so complex. Now, for example, if we take an object have a mass. So we say it is 2 kilogram, 5 kilogram, that's all. So scalars, dealing with scalars is very easy. So the next thing is dealing with vectors, right? Because most of the things, something like force, velocity, acceleration, momentum, they're all vectors. Now, if you understand vectors in general, then we can understand all the physical quantities. If we understand scalars and vectors, so it will make things easier, right? Now, for example, if you want to understand force, let's say how the force and their behaviors. So understanding vectors is enough. Understanding vectors will make make us understand force, velocity, acceleration, and everything. Okay. Okay. So write it down. Scalars. Scalar quantities have only a magnitude, and vectors they have both magnitude and direction. And let's write some examples for scalars and vectors. Okay. So what are the examples for scalars? You can drop in the chat box some examples for scalars. Speed, very good. Mass, speed, mass, temperature, what else? Temperature, good, distance, time. Okay. And current, let's say electric current. Okay. So they are example for scalars and examples for vectors. Can you give me some examples for vectors? Acceleration, good. Displacement, acceleration, displacement, velocity, what else? Momentum. So momentum, we have both linear momentum and angular momentum, both are vectors. And weight, yeah, very good. Okay, so these are examples for vectors. So you may write it down. Okay. Hope you have finished writing this. Okay, and then geometric representation of vectors. Okay, so write down the topic geometric representation of vectors. Okay. Now, for example, I'm going to consider that you are moving to library from your home. Let's say your home or house is A and library is B. So you so you walk from your home house to library in such a path, right? Okay. So you may have traveled a length or distance of something like, let's say, 180 meters, right? So this length, right, the path length is the distance, that is 180 meters. Now, if I consider the shortest path between your house and the library, so that is actually a straight line joining from your house to the library, no? Right? So this distance doesn't have a specific direction because at the initial you are moving to this side, what call northeast, moving to east. At this time you are moving to north, so there is no particular direction for distance. But if I consider the shortest part between your house and the library, so there is a specific direction, right? So what if we call this is the displacement. Displacement is a vector because it have a direction. Okay, so this displacement can be something like 100 meters, right? 100 meters, and the direction now we can say, let's say I draw a horizontal line, and let's say this angle is something like 60 degrees. So I can say now this displacement vector is the displacement from your house to the library. So I can say that displacement is 100 meter. So I can say displacement from your house to library, I'll say from A to B, is 100 meter, and the direction 100 meter in the direction 60 degrees to north from south. I can say towards north from south, not south. This is east, no, from east. Okay. So here, north, east. So now the displacement is a vector, right? But now what I have actually done here, actually is geometric representation, right? Because 100 meter is something like a size of a ground, right? Cricket ground or football ground. But I able to write it down in this screen as a line segment because I am representing this line segment as the vector. So geometric representation. So this line segment might be something like 5 centimeters maybe, right? So in this geometric representation, I can say like 1 centimeter is equivalent to 20 meters. So I have drawn here actually 5 centimeter line segment. That means this AC length, AC is equals 5 centimeter. Okay. Now, if I consider this is actually the displacement vector, so I can say the displacement vector. The displacement vector. I can say denote as AB. A, B. So I put arrow pointing from A to B. So this indicates that vector is pointing from A to B. So this is the symbol how we write a vector. Okay. So now if I consider AB vector, here I consider only AB vector along. So AB vector is A to B 100 meter line. Now this line is 100 meter, making 60 degree angle with horizontal. Okay, so we put arrow from A to B. Okay, I should write this dotted line. Okay, so this is the vector representation or graphical representation. Okay. Okay, so you may note down this. Okay, I'll erase this part. Okay, so here in general, we can say vectors can be represented graphically as arrows or line segments. Okay, the length of the arrow indicates the magnitude of the vector. The length of the arrow indicates the magnitude of the vector. The direction of the arrow indicates the direction of the vector. Okay. Okay, so let's say that this part. Okay, in my geometric representation of displacement vector, I draw a line segment of length 5 centimeter. So it is representing 100 meter from A to B. So here I can say 1 centimeter is equivalent to 20 meter. So this is a 5 centimeter line. Okay, so this is the displacement vector represented geometrically. Okay, good. Now suppose if I want to represent like 50 meter, then what I have to do, I want to draw a line. I want to draw a line that has a length of 5 centimeter in your textbook. Okay, so this is something like 5 centimeter. So it tells that 50 meter of magnitude. Okay, so the length of the line segment or the arrow is proportional to the magnitude. Okay, and then we have the direction. Okay. Okay, length of the arrow or line segment is proportional to the magnitude of the vector. Now, for example, let us say this is, I take one line and I say this is equal to this vector from A, B, let's say. This is equal to, let's say something like, now a force is also vector. So I can say this is 20 Newton, right? And I'm going to draw another line. Let's say I want to represent now 40 Newton. Yeah, 40 Newton. So then I want to draw a line. Let's say a force acting in the same direction, but it is 40 Newton. So here, this is, let's say, Mn. So this is 40 Newton. Okay. So the length is proportional to magnitude, right? If I want to represent 60 Newton, then I want to draw a line which is 3 times this length. No. Okay. So note down this. So here I might have taken, now this might be something like 4 centimeters. So 4 centimeter is about 20 Newton, then 1 centimeter is equivalent to 5 Newton. That means this length, Mn length is, Mn is equals this is 5 centimeter, then this is like, sorry, 1 centimeter is equal to 5 Newton, then means this 4 centimeter, then this is 8 centimeter, right? Okay, good. And the next thing, okay, I write it down first. and then equality of two vectors. Let's say there are two vectors. Okay, so for example, I take AB vector, let's say B, and it has a direction of so AB vector. So this is actually A, B vector, right? The vector also we can denote as something like A, like this, or yeah, usually then we can put here A, right? So both are the same. Now, for example, if you see a line segment and they put something like P and arrow, that means it's a vector. Okay, you can represent either this way or this way, both are same. So let's take there is a AB vector, and then I'm going to take another vector, let's say PQ. Okay, a PQ vector. This PQ, and it has a direction, right? So now we are going to see the criteria or conditions, the requirements for these two vectors to be equal. Okay, so let's write down criteria for two vectors to be equal. Okay, so the first one is I can say both vectors should be same type. That's the first thing. First requirement, both vectors should be same type. Now, for example, if AB is a displacement vector, PQ is also a displacement vector. If AB is a force, then PQ also force. And AB is a velocity, then PQ is also velocity. That's what it means by both vectors should be same type. Okay. And secondly, the magnitude of the vectors should equal. Okay. Now, if I consider these two pictures, now this is has a length, but as we can see, this PQ length is little bit larger, no? This little bit lengthier, so it cannot be equal. So let me reduce the length so that they are in the same size. Let's say, yeah, it's easy to compare like here. Okay, so they should be same side length, same magnitude. So we have P. Okay, so that is the second thing. And third one, I can say, that means here I can say should equal within brackets. I can write AB is equal to the length AB is equal to PQ in geometric representation. Okay, and the third point is both vectors must be or should be parallel to each other. That means I can write AB line is parallel to PQ line. So that's the third point. And fourth, I can say, even if I draw something like this, okay. Now we can see AB is equal to PQ. AB is parallel to PQ. But what happens if I consider this direction, right? So AB is pointing this direction and PQ is pointing in this direction. So what happens then? They are not equal, no, because this vector is in one direction, this vector is in another direction. So they are not equal in this case. Okay. So the last point is I can write both should point in the same direction. Or I just can combine these two statements and just simply write both vectors should act in the same direction. Both vectors are in the same direction. Simply I can write. So if these things are satisfied, then we can say that AB vector and PQ vector are same. So here I can write if all conditions are satisfied, if all conditions are satisfied, then I can say AB vector is equal to PQ vector, right? Okay. So if I'm writing AB equals to PQ, that means AB length is equal to PQ. Also AB is parallel to PQ. Right? These two things contains in this thing. Okay. Okay. If all conditions are satisfied, then AB vector is equal to PQ vector. Okay. And you can take screenshot if you think if you haven't finished, if you haven't tried the notes yet, you can take a screenshot so that you won't miss anything. Okay. Okay. So I'm going to clear it now. So before that, take a screenshot if you haven't finished writing yet. Okay. So we talk about the equality of two vectors, and the next thing, multiplying a vector by minus sign, right? Or you can say simply multiplying by -1, minus sign or -1. Okay. So now let's say we have a vector. Let us take a vector AB. Let's take AB vector here. So AB pointing at this direction. Okay, so that is AB vector. Okay. Now I take this vector, and what I'm going to do is I'm going to multiply this by minus sign. Multiplying by -1 or minus sign. You can simply put either you can put minus sign or -1, both are same. I put -1. Okay. So if I multiply a vector by minus sign, what happens is the only thing happen is its direction will change. I draw another line like this. Okay, so it should be same length. So I take that here, but it is actually pointing in the opposite direction. Okay, so let's take this new vector mn, right? So this vector is, I can name it mn vector, right? So mn vector is equals to what? How? Or equals to what? We take AB vector and multiply by -1, right? So I can rewrite this as mn vector is equals to, multiply by minus, then it is minus a b vector, right? Okay, so I can write this again, mn is equals to, I can write this as now if I consider this, actually now we take this AB vector and multiply by minus sign, means only this direction is changing here. No, in this line only the direction will, in this vector only the direction is changing, so it is actually BA. So then I can write mn is equals to BA again, right? If I consider, compare these two, mn, and because these two vectors are equal vectors, mn, and if I have a BA vector, they are equal. No? We just talk about equality of two vectors. So mn, same length, and they are parallel and same direction. So I can write this like this. Okay, so now if I consider this one and this one, I can write BA vector is nothing but simply minus AB vector. Now this is very important to understand. Okay, so this AB vector is, BA vector is equals to minus AB vector. Note down quickly. Okay, so we can say multiplying a vector by minus sign, we get a vector that is pointing in the opposite direction. So let's write down in words. Multiplying a vector gives a new vector pointing in opposite direction, pointing in opposite direction, pointing in opposite direction with same magnitude, pointing in opposite direction with same magnitude. Okay, the magnitude is not changing, right? Because the magnitude is how big the vector is. So we can see AB and BA both have the same length, right? AB and BA have the same length. So the magnitude is not changing, only the direction is changing. Okay. Okay, and the next thing is multiplying a vector by a real scalar. So let's take a vector here, also the same AB vector. I take AB vector here, A, B. So this is the AB vector pointing from A to B. Okay, and then what I'm going to do is I'm going to multiply this by a scalar. right? A scalar, we know it doesn't have a direction, it's just a number, okay? So something like multiplying with, for example, 2. 2 is a number, it can be 2 or plus 5, 7, 8, 294 or 1.27. So any positive value, okay? Now, then what I get is, I get a new vector. So a new vector pointing in the same direction, but only the magnitude is doubled, okay? Only the magnitude is doubled. I take this here. Okay, wow. I draw a nice parallel line. Good. So I get a new vector. Let's say n. Okay. You can draw the vector like this or even this. Not same. Okay. It doesn't matter. So I get a new vector which has magnitude twice of AB. Now, if I consider this AB and multiplying by 2, then I get mn, right? So actually, I'm writing in terms of length here, right? Similarly, this mn vector, new vector mn, if I say this mn vector I obtained by multiplying 2 with AB vector, right? So then what I get, multiplying by a scalar, I get a new vector pointing in the same direction, but only the magnitude is only the magnitude is scaled by the vector that we have multiplied. Okay, so let's write multiplying a vector by a scalar. Multiplying a vector by a scalar gives vector pointing in the same direction, but the magnitude is scaled, scaled means it is multiplied or something like, let's say you have something like this, let's say for example balloon, and you blow the balloon, so it is enlarged, it's scaled to some big larger volume, right? So similarly, this length is magnitude is scaled by whatever the scalar that you have multiplied by the scalar, scaled by the scalar multiplied. Okay. So now here, if I consider this, okay, mn vector is equals to 2 times AB vector. Okay, I think this thing is clear. If I similarly, if I multiply by 3, what would I get? Multiplying by 3, I get a vector pointing in the same direction, but it's 3 times. No, the length is 3 times. Something like this. Okay. Okay. Okay, clear. And let's do a small example. Okay, so we have to do this. Let us take vector AB, B vector. So this is the AB vector, and I want you to find, draw the vector graphically. I want to draw the vector graphically. This one, multiplying by minus 3, multiplying by minus 3. Okay, so I give you 1 minute. You can try this, and then I will I will help you to get the answer. Yes. Okay, so here we can start from this, right? I take this AB vector, and multiplying by, I'm going to multiply this by minus 1. So what I get, I will get a vector pointing in the opposite direction with the same magnitude, no? Right? So hold on, I get a vector that's pointing in the same opposite direction, but equal in magnitude. Okay, and then what I'm going to do next thing is I'm going to now I get a vector. Now this vector, let's say mn, right? And then I'm going to multiply this vector by number 3, scalar 3. Okay, so multiply by 3, then I'll get this mn into 3. I get a new vector which has a magnitude 3 times this one. No? So we draw here. No, okay, I can draw something like 3 times this length. So something like from here to here. Okay. So I take that here. Okay. So this new vector, I name it as PQ. So I can write PQ vector is equal to 3 times MN vector. Right. And here we know MN vector is equals to minus 1 into AB vector. Right. That means MN. I should write this vector. MN vector is equal to minus AB vector. So PQ vector is equals to 3 into Mn vector is minus AB vector, minus AB vector. So PQ is equals to minus 3AB vector, right? So here also I can write, we wrote earlier that BA vector, earlier we wrote that BA vector is equals to minus AB vector, remember, right? So I can use that here. So PQ is equals to minus 3 into AB is actually minus BA. So PQ is equal to, we get 3 times BA vector. Right? Okay, so we take AB vector and multiply by 3, we get this PQ vector which is equals to minus 3AB. Right? Or else we can say that it is equals to 3BA. So we know AB is this direction, so BA is a vector. BA vector is a vector pointing from here to here. This is the BA vector, right? So BA vector times 3 is PQ vector. 1, 2, 3. Okay, good. Okay, quickly write it down. Okay. And the next one, magnitude of a vector. Now, magnitude of a vector, we usually denote. Now, again, I'll start from, let's start from the AB vector. I can consider the AB vector. So, A, B vector, okay, AB vector. So, the magnitude of AB vector. So, I take this AB vector, taking the magnitude is, we put something like this, 2 bars both sides. So that is actually the magnitude. So magnitude is AB, the length. We only consider the magnitude, right? Okay, so this is the magnitude of AB vector. Now this AB length, now suppose let's say this force, right? So force means this one will have something like AB length is like 5 centimeter. So AB is something like 5 centimeter means, so 1 centimeter maybe we have said something like 2 Newton. So 5 centimeter means something, this will be then 10 Newton. Okay. Because we say that the length of the geometric representation, the length is proportional to the magnitude, right? It can be a force or velocity, acceleration. Okay. Okay, and let's now consider this one. Now let's say we have this AB vector here, A, B vector. So AB vector magnitude is the length. No? So length from here to here. So here the coordinates x comma y. Let's say this is the origin. So we have AB vector magnitude is this length is x squared plus y squared square root. Okay, the magnitude. So magnitude is we consider only how big it is regardless the direction, right? Now, for example, if I consider a vector, right? Here one vector and another vector. Okay. So let's say this is vector A. So I can say this is minus A. Say vector A, and this is minus vector A, right? Or else I can just go with A, B, and B is small. Let's say this is A, B, and then this is B, A. So we know A, B vector is equals to minus B, A vector because they are in opposite direction, right? Or else you can write B, A vector is equals to minus A, B vector. Both are the same, okay? So I consider this formula and considering the magnitude both sides. So AB vector magnitude is equals to minus BA vector magnitude. So AB vector magnitude is actually AB length is equals to, so I can write this minus 1 magnitude into BA vector magnitude, right? So AB is equals to the magnitude of minus 1. So we just consider how big it is regardless of direction. So minus sign is direction. So we neglect that and say the magnitude minus 1 have a magnitude of 1. BA vector is BA. So AB is equals to BA. That is pretty obvious, no? The length AB is equals to BA, right? Okay. Note down this quickly. Okay. The magnitude is also called the modulus or the length of a vector. Okay, the magnitude is also called the modulus or the length of the vector. Okay, because if we take the modulus, we say this is the modulus, right? The symbol is modulus. This actually gives the length, AB length, right? So the length of the vector or modulus. So AB vector modulus. That's how we read it. AB vector magnitude or AB vector modulus. Okay. Modulus of a vector is a scalar, right? Because now earlier we wrote AB vector is equals to minus BA vector. And then taking the modulus, we able to show that AB is equals to BA, right? So it is a vector, it doesn't have a direction, right? Sorry, it's a scalar. The modulus is a scalar. Okay, that means a b vector modulus. This gives a scalar. It doesn't have a direction. A b is a scalar quantity. It doesn't have a direction, or you can say this is a scalar quantity. Multiplication of two vectors. So this part is not in syllabus. Okay. But I hope it will helpful for you if you know about it. Okay, so there are two types of vector multiplications. So one is called dot product or scalar product. Other one is called cross product or vector product. This is not in syllabus, so don't bother about it. But it's good if you have some idea about it. Okay. So if we have, let's say, two vectors A and B making angle theta, right? So the dot product A dot B is defined as, so I write that means A vector dot B vector. This the dot product is defined as A vector modulus. That means how much big it is multiplied with B vector modulus and how much big this vector is, and taking the cos value of the angle between them, cos theta. A dot B is equals modulus A modulus B cos theta. Okay. So now this is also called scalar product because here this is a vector. A is a vector multiplied by B vector. This is a scalar and this is a scalar because we said that modulus is a scalar. This is also scalar. Cos theta is a number, no? Cos theta is cos value of an angle is any value between 1 and minus 1, right? So it is a number scalar, right? So this whole product, this right hand side is a scalar, therefore this dot product is a scalar. That's why we call that, that is also called scalar product. Okay, so one of a good example is, I think you might have learned in your O levels, the work done, right? Work done. So let's say there is a box applying force F in this direction, and it is moving distance this. It's moved from here to here. Let's say that distance is d. It is not small here, d, and this force is F angle theta. So the work done here is actually, if you are, it is actually this. Now I can resolve this force into this direction. We will learn that in a while, the resolving of a vector. So that is this side we have F cos theta into the displacement is d, right? So W is equals modulus of F. Actually, I want to take the modulus of the force, only how much big it is, right? So how much big the force is and how much big the displacement is. So this is, I can write F d cos theta. So you can see these two are similar, no? So here we can see force is a vector, force vector, and displacement is a vector. But this is a scalar, right? So we say that dot product gives a scalar. This is a scalar, right? So work done is a scalar, right? Okay, this is one example of it. Okay, So you may note down this. This is the modulus of force vector. Modulus of force vector. And this D is the modulus of displacement vector. Modulus of displacement vector. Displacement vector. So here work done is a scalar. Work done is a scalar. We know work done is a scalar quantity. It doesn't have a direction. Okay, so that's about product. And then we have cross product or vector product. So let's say we have two vectors A and B, and then they multiply to give a new vector C. Not working. So here we have two vectors A and B making angle theta. So A cross B gives the third vector. So it is this vector. This vector is equals to A cross B. Okay. So and cross product is defined by, let's say, capital A vector cross B vector is equals to A vector modulus into B vector modulus multiplied by sine theta with perpendicular unit vector. Okay, if you don't understand this, don't bother it. Okay, so here A is the A vector modulus, B is the B vector modulus, this is the B vector modulus, and sine theta, sine value of this angle between them, and this is the perpendicular vector, the vector which is perpendicular to A and B, perpendicular unit vector, so something like a unit of 1. Okay, so this is N. Okay, so write down a small topic, unit vector. Unit vector is there in our syllabus, so you should know unit vector. Okay, because I forgot to make a slide for unit vector here. So write down unit vector. So I can write a vector whose magnitude is equal to 1. A vector whose magnitude is equals to 1. So we call that is a unit vector. Now, for example, if I consider the AB vector here, the AB vector, let's say A, B vector. Okay. So I want to find the unit vector in the direction of AB. So let us write that as a question. Okay. Yeah. Or else, yeah, you can write a question. What is the unit vector in the direction along AB vector? Okay, what is the unit vector in the direction along AB vector, right? So I can write, let us say the unit vector is let's say u. Okay, so I take u as the unit vector. So u is equals to, I can write AB vector divided by AB length. AB vector divided by AB length. Now, for example, AB vector is, let's say, 100 meter. So it has a direction this side 100 meter. I'm dividing by length. So length is actually 100 meter. No? So this, which gives 1, right? AB vector divided by AB length. So I can write this as I can write this as unit vector is equals to AB vector divided by AB vector modulus, because AB is equals to AB vector modulus. So you can cross box it. Okay. So this is the unit vector. Okay. You should know about unit vector. It's there in the syllabus. But this dot product and cross product are not in syllabus. But those who are doing mathematics at math stream, they have dot product, but even they don't have cross product. Okay. For those who are doing combined maths, you will learn a lot of things about dot product in your applied mathematics, not in the pure mathematics. In applied one. Okay. Okay then. Let me clear all that. I'll clear this part. So unit vectors, a vector whose magnitude is equals to 1 can be obtained by, you take the vector and divided by its own magnitude. So you get the unit vector along that along the direction of that vector. Okay, and then here so we can use something like right hand rule to find the direction of the AB vector, A cross B. Now here in this one, dot product we call that scalar product, but cross product it's a vector product, because here we get a scalar, right? And modulus A is a scalar, modulus B is a scalar, sine theta is just a number, it's a scalar multiplied by this unit vector. So you take scalar, this whole bunch is a scalar, right? This bunch, sorry, this thing is a scalar, right? You take scalar multiply by vector, right? You take scalar multiply by vector. What happens? We already did multiplying a vector by a scalar. Multiplying a vector by a scalar gives a vector which is pointing in the same direction, but the magnitude is multiplied or scaled by this scalar value, right? Okay. So this whole thing is a vector. And yeah, I would like to tell you one thing that now you might learn throughout our course. I mean, advanced level, you will learn some physical quantities related with some equations, right? Now, for example, the force acting on a magnetic field, the force acting on a magnetic field the force acting on a current carrying conductor in a magnetic field. So we use Fleming's left hand rule. So Fleming's left hand rule is actually derived from this right hand rule, right? So like if there are physical quantities, something like angular momentum, right? One physical quantity is acting one direction, the other one is acting in another direction, and another physical quantity is acting in another direction. The point is, what I want to tell you is, if there is an equation where three physical quantities are acting three different directions, if any formula or expression, the physical quantities are acting in three directions, then keep in mind all three physical quantities are definitely vectors, right? Now, for example, angular momentum. So angular momentum L equals R cross linear momentum. So you will learn this in rotational motion when it comes there. So for now, keep in mind here, this is a vector, this is a vector, this is two vector. So this is actually, we can find the direction of the angular momentum by using right hand rule. Okay. Okay, and also something like moment of force, that too. So moment of force, torque. is perpendicular distance times the force, right? So this is a vector, this is vector, this is vector. So understanding this really helps us to, so that is the point, or main reason why I wanted to explain this. Otherwise, I would skip this and go, because this is not in the syllabus. Okay. So keep in mind, if any equation, okay, so something like rho equals RF, but both three of them are acting in three different directions, then each of them are vectors. Okay. Okay, good. Okay, so resultant of vectors. Okay. So we say the single vector which can be used to produce the same physical effect of system of two or more vectors. So here two or more vectors. Let me write down two or more. Single vector which can be used to produce the same physical effect of system of two or more vectors is called the resultant vector. Okay, or the resultant of vectors. So here in bracket you may write this is the resultant of vectors, or that thing we say the resultant vector. The resultant vector. Okay. Okay, good. The single vector which can be used to produce the same physical effect of system of two or more vectors is called the resultant vector. The resultant vector is the addition or sum of two or more vectors, right? The resultant vector is the addition or sum of two or more vectors. Okay, so let's start from very easy things like addition of two vectors. Right? So here I can say first thing, A part, two vectors are acting in the same direction. Two vectors are acting in the same direction. Okay. So here I can consider, let us consider there is a box. Okay, maybe a table or a box, huge box. Okay, and let's say you are trying to push this with a force, some force. Let's say you are capable of pushing maximum force of 60 Newton, and your younger brother, who is very nice and kind to you, coming and helping you. So your younger brother is pushing with his maximum force 40 Newton, right? So what happens now? Now this one have an unbalanced force. Now due to this force, this box will be accelerated this direction, right? So that is the physical effect, the acceleration. Now I consider the same box here. I consider the same box. Okay. I consider the same box, and let's say your elder brother, who is strong and going to gym and all, have very strong arms. So he is pushing this with a force of 100 Newton, right? So this one will again experience acceleration. Now, if I consider this situation and this situation, both gives the same physical effect, because you are pushing this with 60 and 40 Newton. You are pushing with 60 Newton, and your younger brother is also pushing with 40 Newton. So this is overall effect of something similar to 100 Newton, right? So now we can say this 100 Newton is the resultant of these two. That is easy to understand, no? Yeah, one is pushing with 60 Newton and the other one is pushing 40 Newton in the same direction. So the resultant is 100 Newton. Okay. So here I'm going to say this is force P, and I say this is force Q, and I say this is the force R. And our topic is addition of two vectors, so I'm going to add these two vectors. P vector plus Q vector is equals to P vector is 60 Newton in this direction plus Q vector is 40 Newton in this direction. So we get 60 plus 40, 100 Newton, 100 Newton. So we can see R is equals to 100 Newton because R vector is equals to 100 Newton in this direction. So this is R. So what we get, P vector plus Q vector is equals to R vector. That means R is the resultant of this P and Q vector. So we can write R is the resultant of P vector comma Q vector. P and Q vector. P Q vectors. So plural. Okay, write it down quickly. Okay, the meeting will again finish within a minute. So I'm going to end this meeting now, and then let's start from here. Okay, from where we stop. You can join through the same link. Okay, let me end this meeting now.